Thank you very much for the invitation. It's my first time at Westlake. I'm very happy to visit. And so I will talk about the Harris Venkatesh conjecture for wave one modular form. And so it's based on my own work from 2022, and also on work in progress with Emmanuel. And also, I will explain some ideas due to Robinson. I'm explaining in the world of so, okay. Let me a bit introduce some objects which occur in the setting of the Harris Venkatesh conjecture. So, let me make a few reminders about modular forms and wave one modular forms, and explain why wave one modular forms are very particular compared to higher weights modular forms. So, then you have some level n, and then y1 again the usual modular curve, which parameterizes an elliptic curve with point p of order n. You multiply morphism, and so of course it makes sense over any schema in which n is invertible, but it's the usual notion of the fertile plane, H being the right, and so of course you have the we just add the curve, and so it's a compact curve, and so for any integer k, you have the usual space of hk modular form of one, which is a function f in the plane, which has the second local section on. So there, on the case is before. Okay, that's one way to look at modular of the wave k. Okay, so this is just H0. Now you may ask, why do we consider H0 and not higher homology, right? So what about H1? So it turns out the H1 vanishes as long as k is bigger than 2. So k is bigger than 2, then H1 is k for some degree reason and remember. So the degree of the blind bundle is too high, so H1 has to vanish. But for k equals 1, it's non-zero. So up here, I mean, it can be non-zero. So, that's how we would. So, okay. So for k equals 1, something interesting happens. Can be non-zero. Actually, it has this H1 has the same as it's related to the with the A0. So we have a perfect pairing. We have a perfect pairing. From X1, X1M, X0. X1, X1M, omega, and maybe you have to add vanishing cost to the coefficient field. So it could be over any field. So this could be over any field F on which n is inverted. That n is inverted. Right, you can consider the modular curve over any. Okay, so actually the dimension of these two, because it's a perfect bilinear pairing, has the same dimension. So actually, these two cohomology instances carry the same information. I think they have the same dimension, and also they have the same system of Hecker eigenvalues. So there is some interesting phenomenon. Maybe you could have a weight one Hecker eigenform. So it's an element here which is the eigenvector for Hecker operators, and you will find the same eigenvalues in this H1. Right? So Hecker eigenvalues appear both in H0 and H2. Sorry.
So what do you mean by perfect pairing? Two vector spaces over T.
Yeah. You take them over F.
Your modular curve was defined.
No, it's a modular space, so you can. You could consider it over T, but over any field.
Okay. So in that case, your MK is not defined.
Yes, but it's not. Yeah. Then actually, the right definition of modular form is relative.
Yeah. Okay.
Rather than just functions on the program.
Okay.
Yeah. So sometimes I will promote outcomes that I will give data about which coefficient, which value it is.
Yeah. Okay.
Yeah. So Hecker eigenvalues appear both in the zero and which.
So we have a real analytic analog of this area.
A real analytic. You mean how to describe it? Analytically, right?
Yeah, this is like mark form that you have.
For mass forms. For mass forms, I don't know. I'm not sure for mass forms.
Okay,
yeah, mass forms cannot be described homologically in a simple way.
You still use say like a theory.
Yeah, holomorphic has harmonic mass forms.
Yeah.
There are some ways to describe them, but not also very strong. Okay, so the idea of the starting point of Venkatesh when he developed his conjectures was to explain this phenomenon of spreading Hecker eigenvalues across multiple homology domains. So Venkatesh aims to explain something. Hecker eigenvalues of homology domains. Okay, so he developed really general conjectures in the setting of arithmetic groups. Okay, but here today we are only going to focus on this very special case of wave one from coherent homology. So then in this situation, it's not really also due to Harris. Okay, so I should say the Harris Venkatesh conjecture in this wave one situations. So that's something special about wave one. And another thing special about wave one is that because of this H1 which can be non-zero, you may have some purely Gaussian wave one form. So it's related with the non-vanishing of the H1. So if H1 can be non-zero, one can actually one may have and one can let's say torsion, let's say torsion wave one again multi wave one again. Let me explain orally what this means. It means you can have, you can look again at this H0, but over SP, okay, for some time P, so question part P. And then you may have some sections which do not come from reducing mode, something from character. Okay, so these are wave one forms which do not live in characteristic zero, the classical phenomenon, and it is explained due to this H1. Yes, so somehow the phenomenon of spreading Higgs eigenvalues is related to the distortion, and this could occur in other settings, for instance, the Bianchi modular form for imaginary quadratic field, where you also have spreading from H1 to H2, and also torsion Bianchi class. Many of these situations like that. So now let me be more concrete and try to explain really what conjectures are about. So instead of presenting in the way Venkatesh did using derived echo operator, okay, so Venkatesh is a practice echo operator which moves between H0 and H1. So, derived echo operator. Move from H0 to H1. Usually, Hecke operators are antomorphism, right? Hecke operators preserve H0 or preserve H1. But derived operators move from one degree to another. Right? So Venkatesh did practice these operators and then he made a conjecture about them. So that's how we formulated this conjecture. But today I want to formulate it not using derived operators, but using alpha means. Okay? We will take the point of view of alpha means. And this point of view first appeared in terms of Robinson. So it says due to Robinson. So to be more precise, I will explain the conjecture from the point of view of the Stark conjecture. So more precisely, you can use the Harris Venkatesh conjecture as a kind of Stark version of the Stark conjecture. So what is related to the Harris Venkatesh conjecture is related to Stark's conjecture. So and it could be Stark's conjecture for a very precise for the atomic representation of wave one. Okay, so let me let me explain the classical star conjecture in this setting of wave-wide form, and then derive, motivate the statement of the Harris Venkatesh conjecture. So if you have if is a continuous representation, to get a GMNC, the continuous representation, then Stark describes the leading term of the allocation of actual representation at S equals 0 in terms of some regulators. Okay. For instance, it would be the log description unit in the number field. Kind of determinant. But this means the leading term, right? Okay, so today we are not going to consider any representation, but just some three-dimensional representation. So which comes from the adjoint representation. So, okay, so let's start to be specific. So you have SHE, the segregated form of wave one with the gamma one hand. So this L here means cuspidal, right? The cuspidal again. Okay, and so attached to the G, you have some quantum representation from the gamma group of Q, R of Q, but because it's an Artin representation, it's hard for us to refine it for on gamma group like that. Right, so let's take from gamma R of Q to GL, V being a two-dimensional, vector space. Okay, and for simplicity, to avoid carrying coefficients around everywhere, I will assume G as rational coefficients, so just for simplicity. G has rational coefficients, so integer coefficients. It doesn't match rational coefficients. So V can be chosen to be two-dimensional lattice. So actually, so now what you can consider, now that you have an action on V, you can consider the action by conjugation on the morphism of V. So we get an adjoint representation. So to yes, right? So you have an action of the gamma group on V, and now you act on the endomorphism by conjugation, and actually you act on the trade zero endomorphism by conjugation. Trade zero. So that's called adjoint representation, and it's three, right? This is a three-dimensional space, Z model, right? So yeah. Okay. So So actually, the Harris Venkatesh conjectures are not really about G or G, it's actually about the adjoint. So we are going to consider the fact conjecture of the adjoint. So, here's the map. The first function of the adjoint of G is the R function attached to the scalar representation. Vanishes at order 1 at s equals 0. It's a fact. So I'm going to come back to this fact in a moment. But let's admit that there is a 0 for the 1. And the fact conjecture tells you basically that the derivative at s equals 0 of the cell function is the log of the certain unit. So let me explain more precisely conjecture. So, I need to describe formally what the regulator in this case. So let me do that. Yeah. So that follows that. That Harry used letter for Venkatesh. About which I had very serious so the moment is the mission. Yeah, and the equivalent from this from D or E to F. It's a formal definition, but roughly speaking, what it means is the following. So right here, this is a natural representation. This adjoint is a natural representation from this gamma group. And you basically take the part of the unit of R, which is basically the adjoint to those part. What it means. Right? So ON star is a Galois module, and you want to extract the logical part for the adjoint representation, so that's the way you do that. And that's so up to inverting 6n, one can show that that at dimension 1, so it's 3 of dimension 1. That is 3 of dimension 1 over there. That not you should really invert 6 in it. Okay, so the fact that it has rank 1 is related to the fact that it vanishes at order 1. Okay, so it's a general fact in the more general Venkatesh conjecture that you have from the group like that, which is arithmetic or motivic and something, and this group has a certain rank, and this rank is exactly the same as the vanishing of the adjoint element. But in this very special case of 1-1 only, the order is 1 dimension. Just to point out, and 1 here is the same as this one. So so you have this group, and so one define regulator from that as follows. So we define a regulator map from this kind of unit groups to R, and it's defined by the following construction. So you take an element phi that, so it's a nomomorphism, and we evaluate it on an endomorphism of V, which is defined as the image by the complex conjugation of rho G, where it is a complex conjugation. Okay, so it looks a bit unusual, but well, there is a crucial fact that you use the representation we start with, right? Although we are only interested in the advanced representation, but you still need to use the representation, the two-dimensional representation we start with, construct to quite matrix, right? Which is just you evaluate the whole at any complex conjugation, you get an element on the morphism of V, which turns out to be zero in this case. And then you evaluate you find at the zero matrix. And then you take the log, yeah, right? You take the log. The real log. That's the construction. The log of that real value. That's the construction anyway. Okay, so now can take the start of the lecture. Some conjecture tells you that there exists certain U star in that. Such that the derivative of the point out as you can see is equals to regulation of the real rate of the but you need to basically unique up to root of t. All the derivatives are yes. Now, because it vanishes over one, I think it's just the first derivative. Okay, so that's the classical conjecture. And now, following the idea of Robin-John, we reinterpret the Harris Venkatesh conjecture as a conjecture of this. So, we can say Harris Venkatesh conjecture as a kind of Moski-Planck conjecture. So in some sense, you need to find an equality of which not which is not in R but in LP and then multiple. And it looks very tricky over we don't have a notion of multiple function, the complex. So and then also it's tricky to define a multi-regulator, but there's a way to do that. So let me explain how we can do that. Okay, so but before I can do that, I need to tell a bit more about the adjoint function. And in particular, I will explain why it vanishes at order 1. So, so I need to, for the motivation, I need to tell them. Contracts on the so the adjoint function. So the adjoint is almost like a transfer with itself, except if you remove the one-dimensional factor. But so this kind of thing is called the Rankin-Selberg function. So the Rankin-Selberg methods allow you to express that as an integral. So Rankin-Selberg method tells you basically that up to adding some gamma factor here, so you have to add what I forgot my note. Things like gamma, the square of the gamma factor times some key factor like a polynomial, like some other factors, times the square of the gamma function times the adjoint function for some integral over exponent of g squared, and then e of z comma s y, and then dx dy over y. Okay, where e that s is the real analytic at the time now. So it's not a holomorphic. The Schneider is I mean it's holomorphic it's neuromorphic in S, but it's not holomorphic in Z. Right? Z belongs to the Archimedes thing, and it's has to be well defined in a kind of usual summation similar to the holomorphic Schneider. If you have some value before. Is something okay because I don't have my notes. I think it's like piece of campus. For zero y there's the here went from L. Anyway, that's the information. So it turns out it is holomorphic everywhere in S, except it has a pole at S equals 0 and S equals 1. So holomorphic in S, holomorphic in S, except you will see one here. This is the 0 and this is the 1. And I feel that the functional equation S goes to 1 minus S. And the residue of the zero the depth is that it's a constant. It's that I think important one is that it has a pole of order 1. Okay, so why am I doing all that? It's because you see this adjoint function. Okay, I have to multiply it by a gamma factor. Okay. And so, right, so this gamma has a pole of order 1 at S equals 0. So the squared has a pole of order 2. Right, and here, I mean, okay, let's see here, but here, so that f equals 0 we have a pole of order 1, so this term has a pole of order 1. And so in total, this term has a pole of order 1, so this has to be a 0 of order 1. So what we get is that this is the truth that our function has a 0 of order 1. At s equals 0. And it's true also that the derivative is, if you take the leading term at near s equals 0 of this equality, you get that the derivative is basically, morally speaking, a kind of residue of some kind of Peterson product of G and D times in a society. It's not very rigorous, but right? You can write that as a kind of Peterson product between G and G times an Einstein theory. So, to the point of all that, I mean, yeah, and this proves, by the way, and this proves, so this is actually, this residue is just, for instance, just the Peterson product square. And so the derivative of that joint at equals 0 is nothing else than the square of the Peterson product. That's the concept. Okay. So in other words, this is like the derivative of adjoint L value. You can reinterpret it in terms of pairing and also in terms of Peterson's product. So the idea is that if we want to do some kind of modular version of this derivative, we will start actually with differential pairing. That we construct a kind of pairing similar to that D and G times Einstein. So now let me give the form of Harris Venkatesh. Let me describe properly speaking what Harris Venkatesh is. So so it will be an equality again of this form, right? Left hand side will be a kind of L value, right hand side will be a kind of regulator. So let me first start by the left hand side. So, and in all these stories, so we will take, so let Q and P primes, 0.5, such that value of Q minus 1. So you take 2 primes, P dividing Q minus 1. And this will be, we start with this prime to formulate a conjecture. So the conjecture will be an equality in Z of T. And so let me describe the left hand side. The left hand side is the kind of L function. Okay. L value. And the right hand side will be a kind of regulator. So to define this, the left hand side, we need a key object, which is what is called the Tsinghua class. So, we need Tsinghua class. Okay, so the Tsinghua class is the kind of mod P analog of the real analytic Einstein theory. Mod P analog real Einstein theory. Okay, so the Tsinghua class depends actually not just on P, but also on Q. Okay, actually, it's not really more P, but it's not QP. So this Tsinghua class is a certain class which depends on Q and P. So it depends on Q and it has coefficient dependent on P Z. So it's an element of the dual of the space of model of some global gamma 3 and weight 2. And we value them of and the coefficient is the and tiny good. Okay. If we have coefficient of P and right, to have our gamma 0 Q. Okay, so I'm not going to define it in a precise way. If you want a question, I can do kind of elementary discussion later. But I'm just going to say that we come formally from the covering of modular curve x1 and so here you have a covering whose gamma group is basically Z of QZ star, right? And such a covering can reinterpret it as an element of space. There's a formal way to derive it. Yeah, so the key is that this part here, so it is in this space. Yeah, this space is a Hecker module, right? The Hecker algebra acting on weight 2 and on gamma 0 2 modular form. So the key is that the Tsinghua class is Essenstein. So it's an Essenstein class. In the sense that it is annihilated by some Hecker operators. It's annihilated by certain Hecker operators, which look like something acting on Essenstein theory, like certain Hecker operators in the form TL minus or minus 1, where L is the sign different than so I should say TL minus 1. So L plus 1 here is the wave coefficient of a certain weight with the Stein theory. So that's why we say that the Stein so and in a similar way, this real analytic Stein theory has some Fourier-Bechdel coefficients which look like the curve of 1. They're similar. And so the left-hand side of Harris Venkatesh conjecture is the following. So it depends on the wave one from Q, it depends on the wave one from either G here, and it depends also on Q and on P. And it also depends on the law. However, that contrary, we also choose a specific logarithm, a multitude logarithm. Right? So P divided Q minus 1, therefore Z mod Q Z star is a cyclic group of order divisible by P2. You can find a group morphism Z mod Q Z, and you pick one. Which law? So it depends on choice of law. So left-hand side is you apply the Tsinghua class to a certain weight form, right? The Tsinghua class, you can apply it to a weight picture form, and you get a result in terms of Pz. So you apply it to the following weight picture form is G of Z, and the pure of Pz. Remember, so where B star is the pure form. So it doesn't matter if you have this G, we assume it's a Z variation. So let me, because we're in a situation where it is self dual, there's no need for duality. Right, so this thing is the product of two wave one forms, right? This is wave one, this is wave one. So the product is wave two. So I need to be a bit more precise. The trace from gamma 0 of NQ to gamma 0Q. So this is the wave 1.1, so this is the wave 2, just from S2 gamma 0 NQ. And so if you want to get something in the gamma 0Q, so you just trace down, you put it down to gamma 0Q. Get something. And then you evaluate motion one time. So okay, it looks very highly natural, right? Usually you never do that. I mean, when you have a eigenform and you multiply it with another eigenform, you lose the Hecker eigen property, right? If something is an eigenform, something is an eigenform, you multiply, it's not anymore an eigenform. But nevertheless, it's a cup form. And okay, it has the wrong level, you just put it on. And okay, if you think enough about it, this term is very similar to what can be used. Kind of pairing of G and G, and G, and then it's a shine through. It's kind of the analog. And actually, it's so analogous that John is recent purpose is notation, but I think it's conceptually significant. John finds quantity the Peterson product, where the Peterson product of G mod Q. I'm not using it doesn't show the discrete. Okay, I just project onto the mod Q. For him, it just works with correction is M of Q delta star, but it's not essential. But the point is that John interprets quantity as the square of the Peterson norm mod. It's the first time for consider that mod Peterson product. Never seen that. So okay, so anyway, that's the left hand side, and the right hand side is very similar to what we had in the span conjectures, but pretty easy. So instead of a real regulator, you have a multi-Q regulator. Right hand side. Okay, so you have a small Q, most Q regression to the related from to the multi-del. It's just kind of phi, right? Phi is a kind of home Galois variant from at the Morphism B to the group of units, and you just take a certain form like that and evaluate it on some element of trace zero, which is not related to the complex integration anymore, but the Frobenius in Q. So rho G from the Frobenius element. So before, if you had the complex conjugation, the cure is replaced by the Frobenius, very natural, except it's not really trace zero, but this matrix may not be trace zero, so you have a clique, which is equivalent there. It's actually 2 times rho of 3 minus it's forced to be trace zero. So the matrix is not trace zero, you just basically scale, then minus the twist becomes phase zero when you evaluate on phi. That's the regulator. And so here you go. So conjecture Harris Venkatesh in 2017, correct? So that is the unit. The unit of Harris Venkatesh in lab, such that, and also that it explains the constant, there, which depends only on G, depending only on G. So that for any Q and P prime as before, we have that the left hand side equals the right hand side. So the left hand side kind of more business we call it is C times so the T times that is equal to the regulating of this unit. Very similar. So instead of having a Peterson product, which is a real number, equals to a real regulator and get everything but possible. Okay. So now I wanted to explain a bit state of the art on that. Oh, I don't have much time, but roughly speaking, yeah. Okay, so roughly, we know we have result on the Harris Venkatesh conjecture roughly when we have result on the Planck conjecture. So the two conjectures, the Planck conjecture and the Harris Venkatesh conjecture, somehow carry the same kind of difficulty. So right now, we only have the note. Dihedral is when G is dihedral. It means the use of the Hegel character of a quadratic field. It's what we call the delta space. From the quadratic field of the certain Hegel class. So it could be real or imaginary quadratic. The two cases are very different. I'm not saying we know how to prove it in any case where it's dihedral. So far, we have some restrictions on dihedral examples we know how to solve. So when I say result, both on the Harris Venkatesh and some. Isotherm is known in all the cases where G is induced, right? But it's not known when G is an exceptional wave quantum, exotic wave quantum. And similar to the Harris Venkatesh conjecture, we have result only in the dihedral. Okay, so let me citing a few works on the a few results on the Harris Venkatesh conjecture. So it's due to work by 400 or so. What were this is the data correspondence. Then myself in 2022, I have a new approach, in some way it's stronger, using threefold product definition. Threefold product applications. I have some results which go beyond them, but also, yeah. And then by Robin John, in 2023. And actually, I don't know much about methods, so I won't describe it. There are three kinds of work on conjecture. I want to finish by just saying that Robin, in a recent preprint, combined both the star conjecture and the Harris Venkatesh conjecture in one single conjecture, and proved it continues. So, finally, describes the final conjecture. So, preprint is for like the Harris Venkatesh conjecture and the star conjecture, or something like that. And so, let's see. Then there exists certain unity in VAR, such that we like improvements what as before, state A, the real square root product P is derivative of is the real regulator of P, and P mod QP square root product according to John is the most QP regulator. So A is Stark, B is Harris Venkatesh. But the key point is that we have combined the two with a single element of that. But before we had one element for one unit for Stark conjecture and one unit for the Harris Venkatesh conjecture, and now we have the same unit for both. And so this is called Stark plus Harris Venkatesh. I think it's very nice to put on the same footing. To put on the same footing two different conjectures, but which both are about the actual element. And now the last one, John proved this in the case, in certain dihedral case. So, even in the same paper, this is paper with stated. So the conjecture is proved for any dihedral wave form attached to a character of an imaginary quadratic. So sometimes the imaginary quadratic case, dihedral case is much more. We have much more complete results than the real quadratic case. So that yeah. Yeah. So there may be some partial results from the real quadratic case. And take this result. And I think that, yeah, that's all I wanted to do.